Okay, guys, welcome. Today we're going to talk about the Miller-Rabin test. Okay. Now, in a previous video, we talked about RSA encryption, and that requires us to quickly generate very large prime numbers. Now, one way to do this, since we can't really efficiently generate a sequence of prime numbers, is what we could do is just generate some random numbers and test to see them if they are prime, right? And of course, if we have a method that's fast enough to generate numbers and test them for primality, if it's fast enough, you won't have to spend too much time on this. Okay. Now, the main idea of the Miller-Rabin test is, of course, to do that, right? So the main idea is that if n is prime, then z mod n should only contain 2 square roots of 1, right? And of course, they would be 1 and -1. Otherwise, if there's others that exist, we can find them with a pretty good likelihood, but it's not, of course, a guarantee, right? So the Miller-Rabin test is probabilistic to an extent, right? So when you do this thing, you can only be very, very sure that what we're doing will lead to an optimal result, not that it's a guarantee, right? But usually that's good enough. Okay, so let's look at the following theorem. So if n, which is positive and greater than 1, is an integer, and there exists 2 numbers x and y such that x squared is congruent to y squared mod n, but x is not congruent to plus or minus y mod n, then n is composite, right? And this is going to allow us to sort of use this idea, right? If n is prime, then zn should only contain 2 square roots of 1, namely 1 and -1. Now, if n is bigger than 2 is prime, then we can write n uniquely as 1 plus 2 to the k times m, right? And of course, it follows that if a is between 1 and n, then a to the n is congruent to a mod n by Fermat's little theorem, okay? And of course, this means that a to the 2 to the k times m is congruent to 1 mod n, okay? Okay, so let's consider the sequence in Z mod n, right? Where we take a to the m and we keep squaring it. So we have a to the m, a to the 2m, a to the 4m, and so on. And we just get this sequence of a to the powers of 2 times m. Okay, now since a to the 2 to the k times m is congruent to 1 mod n, the previous term squared, since that gives us 1, it has to be plus or minus 1, right? And of course, this is because we're choosing n to be prime, right? So if z mod n is such that our n is a prime number, then our sequence is either all a sequence of 1s, or the other option is that we get some numbers and then we get a -1, which once we square it becomes +1, and then it's 1 and forever, right, until the end. And of course, if we have a sequence that's not of either of these two forms, then we know that our n has to be composite, or at least the Miller-Rabin test tells us that n is composite. So if we choose A and we compute this sequence, we may be able to tell if n is prime or not, all right? And I think what will be helpful here is let's look at a nice small example, and then we'll be able to determine if the Miller-Rabin test correctly identifies the number as a prime, and we'll also sort of see the process at work here. So we're going to do this for when n is equal to 5. Okay, so we're going to determine if the Miller-Rabin test correctly identifies 5 as being prime. Okay, now we can write 5 in the form of 1 plus 2 to the k times m if k is 2 and m is 1, right? So then that gives us that k is 2, m is 1. We get 1 plus 2 squared times 1, or 1 plus 4, which of course is 5. Now we have 3 choices of a, because we need a, remember, to be bigger than 1, but less than n, right? And we're in n equals 5. So we need our a to be either 2, 3, or 4, okay? Now let's check for each of these. So if a is equal to 2, well, then a to the n should be congruent to a mod n by Fermat's little theorem. And of course it is, because if you look at 2 to the 5th, that's equal to 32, which is 2 mod 5. So of course that still holds here, right? And that means that 2 to our 2 to the k times m, which in this case is 2 squared times 1, is equal to 2 to the 4, is 1 mod 5. So now let's look at the sequence of a to the n all the way up to 2 to the k times m. Well, again, remember that m is 1, so we're just multiplying this essentially the powers of 2. And of course, here our sequence only has 3 terms. We only have 2, 4, and 16, right? So of course we have 2, 4, 16. First number, 2 is still 2 mod 5, but 4 mod 5 we could think of as negative 1. And of course 16 mod 5 is 1, right? So if we were to carry out the test here, we get 2, negative 1, and then 1s for the rest of the way, right? If we were to keep going. So this correctly predicts that n equals 5 is prime. Okay, for a equals 3, we should be able to do the same thing. And of course, a to the n, which in this case is 3 to the 5, is 243, which is 3 mod 5, right? And if I raise 3 to the 4th power, which is my 2 to the k, or 2 squared, times m, we get 81, which is 1 mod 5. Now, if we write out this sequence, we get 3, and then 9, which is negative 1 mod 5, and then we get 81, which is 1 mod 5, right? So then our sequence is 3, negative 1, 1, so on and so forth, if you were to keep going. And this, again, will predict that n equals 5 is prime. Right, and then finally, when you do this for 4, right, these both still work out as they should. And then we get 4, 16, and 256, which mod 5 would be negative 1, 1, 1, so on and so forth. So this will also correctly predict that n equals 5 is prime. Right? Now, of course, this will not always occur without fail. As we mentioned, this test is probabilistic. And in fact, for some strange values of a, which are known as Carmichael numbers, no choice of a will work, right? So that's one interesting thing that comes into play here. But now the Miller-Rabin test gives us a way to quickly test if a number is prime, right? So that's what we're going to use moving forward. All right, so that concludes this video on the Miller-Rabin test. I hope you enjoyed, and I will see you next time.